Okay, so in the last video, we learned about the chain rule, okay? The chain rule, which said if you had a composite function, okay? You had a composite function f of g of x, okay? Which is, we'll define that composite function as p of x, then p prime of x will be the derivative of the outside function with respect to the inside function times the derivative of the inside function with respect to x. Okay, so we did that last time. Now, one really good and helpful implication, okay, of the chain rule is in a very useful technique, okay, known as implicit differentiation. Implicit differentiation. Okay, so for the entire time we've been learning about derivatives, we have been doing explicit differentiation, where a function y is given explicitly as a function of x. Okay? Meaning that we've been differentiating functions such as y equals 2x squared plus 5, y equals 2x minus 3 over 3x minus 2. So you have the y on one side and x on the other. In other words, we have solved the equation to express y as a function of x. So these equations are explicit. We have defined the function explicitly with all the y's on the left and the x's on the right. Implicit differentiation will help you solve x squared, stuff like x squared plus 2y equals 9, where the x's and y's are mixed on one side, and in most cases, the equation will be extremely difficult to solve for y, almost impossible. So we're going to use a trick known as implicit differentiation. So we're going to walk us through with the generic equation of a circle. So you might be thinking, well, a circle is not a function, okay? And that is the magic of implicit differentiation. You can find derivatives of non-functions. Any equation that can be graphed on the xy plane, you can take the derivative of using implicit differentiation. If it's defined like this, okay, if it's defined explicitly, then you can just take the derivative. In most cases, it will be a function, and you can take the derivative with either the chain rule, product rule, quotient rule, and all the basic rules, okay? So we're going to try implicit differentiation with this function, x squared plus y squared equals 9. Which is basically a circle centered at 0 at the origin, 0, 0, with radius 3. Okay? So first what you have to do is take the derivative of both sides with respect to x. So we're going to take the derivative of x squared plus y squared of both sides. We're going to take the derivative of both sides with respect to x, since we're trying to find dy dx, the little change in y or the little change in x. The derivative, the slope of the function at that exact point. Okay? The slope of the equation at the exact point. Okay? So for the first term on the left, so this will just equal 0. So we're not even going to have to worry about the right. But for the left, well, the first term on the left, x squared, well, I can differentiate normally. That'll just be 2x. Okay? However, the second term on the left, y squared, well, y is not written in terms of x. We're trying to find a derivative in terms of x. We're taking the derivative with respect to x. So if you really understand how the chain rule works, this will be quite easy to understand, because what we're going to do is literally apply the chain rule over here. So we're going to first take the derivative of what we'll call the outside function y squared with respect to the inside function y. Okay? So we're going to take the derivative of y squared with respect to y, since y itself will be our inside function. So the derivative with respect to y will be 2y, power rule. And we're going to have to multiply it by the derivative of y with respect to x, which you literally write as dy dx equals 0. So what we did here, just gonna isolate this, is that since the variables did not match, x and y don't match, we use the chain rule, okay? By taking the derivative with respect to y, okay? First, by taking the derivative with respect to y first, and then taking the derivative of y with respect to x, the outside function with respect to the inside function, y. So we get 2y dy dx. Okay? And that is the crux of implicit differentiation. Okay? Being able to understand why we can do stuff like this. And if you were to, and what we're going to do now is isolate and solve for dy dx, since that is what we want to find in the first place. So we're going to subtract 2x from both sides and divide. Cancel, cancel, and we get dy dx equals negative x over y. Now, keep in mind that the derivative of this function, unlike the explicit functions that you have seen before, depend on both the x and y coordinate, okay? So if I were to draw a circle, okay? So coordinate plane, it's not very straight, but we're gonna have to live with it. This is point x comma y. This is the equation of the circle. It's 3. Okay? Well, this is not a function, okay? It's not a function, which means there is more than one y value for each x value. This is x, this is y, but there's another point with the same x coordinate, x negative y. And if you were to draw the tangent lines to both of them, which would kind of look like this, you could see they have really different slopes. In fact, one is the negative of the other. So in non-functions, usually you'll see a y term, and it's important to keep in mind that when you differentiate implicitly, you have the possibility of having a y term along with an x term. So we're going to do 2 examples, okay? A couple of examples. And delete. So we're going to do the function x cubed plus xy minus y squared equals 8. Okay? So first, we're going to take the derivative with respect to x of both sides. Okay? So we're going to take the derivative with respect to x on both sides. Well, the derivative of 8 is 0, so I guess we're going to replace this with a 0 over here. Now the variables agree over here. We have x and an x, so we're going to differentiate as normal and use the power rule. 3x squared. Okay? 3x squared plus, well, the derivative of xy is a bit tricky, but if you can see an obvious use of the product rule, then it's not so tricky. Okay? So you can use an obvious use of the power rule. F prime 1 times g, y, plus g prime, the derivative of y. Well, we're going to take the derivative of y, 1 times dy dx. Okay, so the derivative of y with respect to x will just be dy dx times the first function, x, minus y squared. Well, we're going to first differentiate with respect to y. So minus 2y, power rule. But we're going to have to take the derivative of y with respect to x. So that gets us dy dx. Okay? So we rewrite it now without the parentheses. Plus x dy dx minus 2y dy dx. We're going to get all the dy dx's on the right. Okay? Or on the left, it's a preference. Okay? So we have 3x squared plus y equals 2y dy dx minus x dy dx. And what you can do, you can literally factor out dy dx out of the answer. So this gets us dy dx times 2y minus x. And we're going to now divide by 2y minus x, get dy dx equals 3x squared plus y over 2y minus x. And we are done. Okay, so we're done with this one. So next we're going to do another type of problem. Okay, so we can do tangent lines with this stuff as well. Okay, it's literally putting the xy coordinates into the equation and solving. Okay, so let's do one of that. Okay, so we're going to have tangent. Well, let's do this one. Okay. Which one? Tangent of x plus y equals x. When I find a tangent line to the curve at point 0, 0. Okay? So first, what are we going to do? What are we even going to do? So for the left, okay, we're going to take the derivative with respect to x on both sides, since that's a must for our implicit. Implicit differentiation, take the derivative with respect to x on both sides. So, and we have a non-constant term on the right, so we're going to actually have a value on the right. Okay? So to take the derivative with respect to x on the left, okay, we have to apply the chain rule. X plus y will be our inside function, and the tangent of x plus y tangent function will be our outside function. So we're going to take the derivative with respect to the inside function, so that's secant squared x plus y times, well, the derivative of x plus y, okay? So the derivative of x plus y will be x, okay? Not x, the derivative of x will just be 1. 1 plus derivative of y with respect to x is simply dy dx. dy dx, and the derivative with respect to x, again, is 1. Okay? So we can distribute, so secant squared of x plus y plus secant squared x plus y dy dx. Okay? And what we get out of here, we can bring this to the right. So we get secant squared x plus y of dy dx equals 1 minus secant squared x plus y. And we're going to divide by secant squared x plus y on both sides. And we get this. This is our answer. Well, you could have noticed another way we could have done it. On here, well, you're going to simply just divide by secant squared x plus y over here. So we get 1 plus dy dx equals 1 over secant squared x plus y, which you might recognize, as 1 over secant is cosine squared. Okay, so you get cosine squared x plus y. And you can subtract 1, and you get dy dx equals cosine squared x plus y minus 1. And you could verify using trig and trigonometry that both of these functions, both of these expressions are equivalent. But we're still not done, because we want to find the equation of the tangent line at point 0, 0. Okay? So if we want to plug in x and y, so we get dy dx, the slope of the function at point 0, 0, we get cosine squared 0 plus 0 minus 1. Well, the cosine of 0 squared, okay? So cosine of 0 is 1, 1 squared is 1, minus 1 is 0. So turns out that dy dx at 0, 0 is actually 0. So we have a horizontal line, which makes getting our tangent line a lot easier. It will just be y equals 0. We have our y coordinate over here. So we can just plug it in here, and since we know it has 0 slope, we get y equals 0. And that is our answer. That is our answer. Okay, so you get y equals 0. So I'm going to do one final problem. Okay? One final problem. Okay, and this one is actually this one's a good one. Okay? So if we have an equation x squared y squared minus 2x equals 3, what is d squared y over dx squared? The second derivative of this thing. Okay, so as we did with explicit functions, let's first find the first derivative, dy dx. So to find dy dx, you have to first take the derivative of both sides. X squared y squared minus 2x equals 0. The derivative of a constant is 0. Okay, fair enough. So we do the product rule on the left side with the first term. So we get f prime g plus g prime So we have 2y dy dx. We're differentiating with respect to y times the derivative of y with respect to x. So we have 2y dy dx times the first function, x squared. Okay, so that's the derivative of the first term, minus the derivative of 2x will just be 2. So we have this as 2xy squared plus 2yx squared dy dx minus 2 equals 0. And if we were to bring the 2 on the right, we have 2xy squared plus 2yx squared dy dx equals 2. And if we isolate dy dx, okay, just an equation, we get 2 minus 2xy squared over 2yx squared. And this will, we're going to simplify it since it will make things a lot easier for what we're going to do next. We're going to take out all the 2's. We have 1 minus xy squared over yx squared. We just simply factored out a 2 and took out the 2 from the denominator by cancellation. Okay? So, what about d squared y over dx squared? D squared y over dx squared. So we're going to find the derivative of 1 minus xy squared over yx squared. So this will be an implicit problem right here. So a quotient rule / implicit, okay? So we have f prime, okay, so that's 0, 0 minus, well, we have more product rule. We have product rule stuff, okay? So 0 minus f prime 1 g 2y dy dx so f prime g plus g prime, wait a minute, f prime g by itself, okay, f prime g plus g prime, so now we put 2y dy dx, g prime f that was only the first term, okay? Minus 1 minus xy squared, 1 minus xy squared, so the f prime g minus g prime f, so f g prime. So this will be another application of the product rule for the denominator. So we have f prime, so we have dy dx prime g plus g prime f 2xy all of that over g squared. So we get y squared x to the 4th. What I'm going to do is copy this whole mess so that we can get some blank space. Okay. Okay, so we were right over here. Okay. So we just applied the quotient rule with a good helping of product rule in it. And now we're going to have to simplify this into something we can even begin to understand. Okay, so in the top we have negative y squared minus 2xy dy dx, 2xy dy dx, 2xy dy dx looks about right, minus, well, this will be painful. Well, we're going to FOIL it out, okay? first outer, first outer inner, oh my good God, and last. And last. So this 2x squared y cubed. Now this will be a gold mine for algebraers. Okay, so we have to be careful. Okay, so let me just check. Okay, so it looks good. Over y squared x to the fourth. Okay, so now what we're going to do, well, what I'm going to do at least, is bring together all of the dy dx's. Okay, so you have negative y squared. So it's going to minus 2xy dy dx minus x squared dy dx minus x squared dy dx plus x squared, well, x to the cube, y squared, x cubed, y squared, dy dx, and everything else. Okay, minus 2xy plus 2x squared y cubed. All that over y squared x to the fourth. What I'm going to do this for is so that we get over here. Okay, so I'm going to move all this to the right, and what I'm going to do is factor out dy dx. Okay, so we're going to factor out dy dx minus 2xy minus x squared plus x cubed y squared. You got to be careful about algebra. Mistakes. Y squared x to the fourth. Now, you know why I factored it? Because we want the second derivative to be with respect to x and y. This over here is dy dx. So guess what? We're going to have to substitute that entire expression inside here. Okay, so as if we thought we were in the home stretch, but we have to put this original expression in place of here. Squared plus, forgive the terrible lack of space, over y squared x to the fourth. And you can simplify this, of course. You can distribute and multiply the two polynomials in the numerator, okay? Add it all up, and that will get you, okay? So you can simplify this expression, but this expression really is the raw form of the second derivative. So taking the second derivative of an implicit function is an absolute nightmare.